we proposed a novel approach that combines the advantages of both model-based and learning-based frameworks to achieve consistent and robust locomotion. By utilizing residual modules constructed by learning-based method with nominal model-based controller, the control performance can be improved in environment with high uncertainties, while also achieving consistent performance in out-of-distribution situations. Our framework consists of residual modules, which are integrated with each corresponding part of the model-based framework, the footstep planner, and nominal dynamics model. Each module is aimed to modulate the output from the corresponding nominal module for complementing performance degradation caused by a model mismatch. A key feature of the proposed method is that each residual module is sequentially structured, utilizing reinforcement learning or supervised learning. By utilizing a modular structure and selecting the appropriate learning-based method for each residual module, we can enhance sample efficiency without compromising performance compared to other hybrid methods. We conduct experiments in the real world to investigate the effects of each residual modules. The scenario is to give system some uncertainties and see how the system behaves with or without the proposed framework. This video shows how a nominal MPC controller works. As seen in this video, vanilla MPC fails to maintain its posture under the given model mismatch. Next, only residual dynamics module is applied to nominal controller. The robot successfully adapts to the model discrepancy immediately after the payload is applied. However, over time, the payload makes sagittal swaying motion, resulting in failure with additional disturbances. In contrast, with both residual dynamics and footstep module, the system successfully controls locomotion despite heavy payload and various disturbances. This video presents a slowed-down version of the previous one. After an external disturbance is applied, the residual dynamics module detects the discrepancy in roll directional angular momentum, while the residual footstep module shortens the stance duration and adjusts the foothold position. We also conducted experiments to investigate the system's behavior while the robot is accelerating up to 1 meter per second. As shown in the video, the residual footstep module immediately shortens the stance phase when the robot is commanded to run faster. Furthermore, after a disturbance is applied, it adjusts the foothold position in the Y direction. Next, we investigated whether the residual module can alleviate control parameter dependency. In this scenario, the robot is commanded to follow the velocity command, but with different cost function weight setups. As seen in the left figure, vanilla MPC exhibited significant variations in success rate and tracking error depending on parameter settings. In contrast, our proposed method demonstrated consistent performance regardless of parameter changes. The proposed method also demonstrated relatively consistent performance in additional experiments, even without weight randomization. We also validate whether our proposed framework offers improved consistency compared to existing approaches when the system encounters totally different conditions from those in the simulation environment. During the learning process, only the weight of the robot's trunk was randomized. However, in real-world scenarios, 2-3 kilograms payloads were applied to both right front and hind legs. We designed an end-to-end RL controller as a baseline. When no external payloads were applied, baseline RL tracked the given velocity commands properly. However, the velocity tracking performance of the baseline RL method dropped significantly under conditions where external payloads were applied to both feet. This video shows how the proposed method tracks the command in normal condition. In contrast to baseline RL, the proposed method successfully tracks the command despite the applied payload. In last, we conduct an ablation study to analyze how the design method of each residual module affect control performance and learning efficiency. The robot is commanded to traverse rough terrain with different controller and residual module designs. As seen on the left, our framework consistently achieved a high success rate and tracking performance, while most baseline methods exhibited greater fluctuation in performance. Moreover, our method also demonstrated the stable and fastest convergence during training. By selectively applying proper design method based on the characteristics of each module, it is possible to achieve high learning efficiency and stability while still maintaining improved control performance. Thank you for watching.